All right. There's different levels we understand things. One of the levels, it could be, just your basic pattern recognition. Basic pattern recognition would be AB plus CD pattern, right? But sometimes I leave it more open-ended. I want you to show me more, if you can. So, things like state, ionic equation, net ion equation, etc. But this gives us an opportunity to do some more review of Chem 1A. So, for example, calcium carbonate, everybody should know the formula. If you're a little rusty with the formula and the charges, then you better start reviewing those today. Because if you get the formula wrong or the charge wrong, you're going to lose a lot of points in this spot. And so, however you do to remember, calcium carbonate, CaCO3, do it. But calcium carbonate, what is that? Is that a solid, liquid, gas? What is that? This is solid. Ionic compounds, for the most part, are all solids. But there's water around. Where's the water coming from? The sulfuric acid. Sulfuric acid is the solution of H2SO4 with water. And so there's plenty of water around. So will calcium carbonate dissolve in water? No, because carbonates are all insoluble except for group 1 and ammonium. And so you'd say, oh, okay, this is an insoluble solid. And so all that stuff you could have memorized, but we don't want to have to memorize every single thing. And so there's certain things we could understand a bit more on theory. Not full theory where we're doing calculations and that kind of stuff, but a little bit of theory. So for example, a little bit of theory here would be, well, what does calcium carbonate, when you visualize calcium carbonate, what comes to mind? And so in other words, we want like some structural stuff. So let me ask you, what's the Lewis structure for calcium carbonate? How do you draw or write the Lewis structure for calcium carbonate? Three oxygens sticking out like this? With the calcium like this?
Attached to the carbon.
Attached to the carbon like this? Well, something like that? You agree?
Yeah.
And so calcium carbonate is an example of an ionic compound or covalent or molecular compound? Ionic compound. And for ionic compounds, we've got to show the ionic bond. Is this ionic bond here, this line that joins calcium and carbon? Is that the ionic bond? Or is this an ionic bond here too? These ionic bonds? And so we do a little bit of Chem 1A review to try to better understand calcium carbonate. For example, why do you think calcium carbonate might be insoluble, but something like sodium carbonate soluble? For example, if this were sodium carbonate's a white solid also. But if this were sodium carbonate, I would have written not solid here. I would have written sodium carbonate AQ, because as soon as I take that white solid sodium carbonate and mix it with HCl, the first thing it does, even before a chemical reaction might occur, is it dissolves in water. And so you could have all this memorized, but we don't want to memorize everything, and so we try to get the two-pronged approach, a little bit of theory to ease the memorization load. And so what we want to do is we want to start understanding things like the composition, the structure of calcium carbonate. Well, the composition is here. What is the structure? And so is this the structure of calcium carbonate? No, because it's not the structure. When we're dealing with ionic compounds, how do we show an ionic bond? Do you recall? I think it's chapter 12, 11 or 12, how to show an ionic bond. You show an ionic bond quite a bit differently than you show a covalent bond. You don't show them the same way. And so how was an ionic bond shown versus a covalent bond in a Lewis structure? Right, it's in brackets. In fact, the answer is that's a trick question, because ionic bonds aren't shown. Did you know? We never show ionic bonds. All we show is this. we have two ions, calcium ion and carbonate ion, and the ionic bond is here. The ionic bond is the bond holding the positive and the negative species together. That electrical, what we call electrical attraction. But, the Lewis structure for carbonate, this is not right. The Lewis structure, carbonate actually has covalent bonds in there. Covalent bonds we show with a line like this. In fact, if you recall carbonate, they're going to be resonance forms for carbonate. You have two single bonds and a double bond. And if you take all those resonance forms and then do what? Hybridize them, or not hybridize, that's the wrong word. You take all those resonance forms, you come up with the resonance hybrid. You guys remember the resonance hybrid? And so the resonance hybrid for carbonate is all the bonds are equal. They're 1 1/3 bonds, right? Bond order. And this whole thing has a -2 charge with 2 lone pairs fixed on here and 1 lone pair floating. What's the geometry of this ion? Trigonal planar. That's good. And all the bonds are equal, so this is very symmetric. It's a nice symmetric triangle. And this ion is going to be held together to this ion by what we call an ionic bond. The ionic bond is just the proximity of the calcium and the carbonate. And we put them next to each other. But we know that ionic compounds, do they form molecules? Is this a molecule of calcium carbonate here? Do ionic compounds form molecules? No. Ionic compounds form, not covalent lattices, the other one. Ionic lattices. And an ionic lattice is, if I have a positive sphere, the positive sphere is going to want to surround itself by as many negatives as possible. And so let's do that. Throw in another carbonate here, another carbonate here, another carbonate here. So we get 4 in the plane, and then maybe 1 on top and 1 underneath. And each carbonate will want to surround itself by as many positives as possible, and we call this structure the ionic lattice. And so what holds together the ionic lattice? Ionic bonds. And so this is the lattice for calcium carbonate. This lattice kind of looks like, if you look at the calciums, which are the white, the carbonates are these triangular things here. The triangular carbonates kind of distort the structure, so it's not a cube. You guys remember the cubic? We had what? We had face-centered cubic, body-centered cubic, and primitive or simple cubic. This one looks like a face-centered cubic lattice of calciums, although it's not a cube, with the carbonates stuck in the, what we call the octahedral holes of this. And so this is a calcium carbonate structure. Now, why is this hard to dissolve? Well, it's hard to dissolve because the calcium ions are hard to pull off, the carbonate ions are hard to pull off from the lattice. Why are they hard to pull off? Because if I pull off a calcium, am I just breaking one ionic bond? No, I'm breaking multiple ionic bonds, right? It's not just one bond. And if you go back to chapter 1, do you guys remember Coulomb's law from chapter 1? Or does it sound familiar? What's the most important force in chemistry? The most important force in chemistry are in fact, pretty much all we look at are electrical interactions, electrical attractions. And so calcium carbonate, this is a fairly stable lattice. There are two things that the force of attraction or force of repulsion depends on. One, the charge. The bigger the charge, the stronger the force. Two, the distance. The distance we think in terms of size. So the smaller the ion, the stronger the force. And we usually do that as a composite. We look at the charge to size ratio. You know, big charge, small size means big charge to size ratio, which means very reactive. And so in this case, yeah, the calciums and the carbonates are reacting towards each other. In other words, they're going to form a strong bond here. That strong bond is hard to break apart, and therefore this isn't very soluble, whereas sodium carbonate is quite soluble. Sodium carbonate, no problem dissolving that. Now, why would sodium carbonate dissolve and calcium carbonate not dissolve? Can somebody tell me? Smaller charge. Sodiums are +1 versus calcium's at +2. So pulling a sodium off here, you don't have as strong of an electrical force pulling it, electrical attraction. And so that's the two-pronged approach. The approach is a bit of memorization. You memorize the solubility rules, and a bit of theory. We try to understand the solubility rules based on simple structural things that we learned in Chem 1A. Not simple. It's simple once you learn it, but if you don't apply it, then it's very difficult, right? And so we know that this lattice is going to be fairly strong. That doesn't mean calcium carbonate won't react. If we have something like sulfuric acid can attack this lattice. You know, water can try to attack it, but it's not going to do anything. Water's not going to. But if you throw in some sulfuric acid in here, the sulfuric acid will attack the lattice and break it apart. And so we can get the calcium carbonate to dissolve in sulfuric acid. Well, you know, each time we should try to reinforce the concepts that we learn in Chem 1A, you know, because repetition helps. And so for sulfuric acid, what's a Lewis structure for sulfuric acid? Is sulfuric acid an ionic compound like calcium carbonate? No. And so we come up with the Lewis structure for sulfuric acid. And what does it look like? Maybe a sulfur as the central atom. Yeah? 4 oxygens attached to it. That. Where do the hydrogens go? On the oxygens. Does it matter which two? Should I pick opposing or adjacent, or does it matter? It does not matter because I know the structure. Sulfur is going to be not trigonal planar like this. This sulfur should be tetrahedral. And so there's no such thing as adjacent and opposite. All sites are adjacent to each other with an angle of 109.5 degrees. And so it doesn't matter where I put the second hydrogen because they're all the same. Now, we have some choices here, and we could leave sulfur with an octet, but if I go to Wikipedia and I look at the structure in Wikipedia, Wikipedia has this. In fact, this is the way I learned sulfuric acid too. Wikipedia has 2 double bonds and 2 single bonds in the sulfur. It's still tetrahedral, right? Yeah. Yeah, still tetrahedral. So why would they do this? Because this has an octet. This has what we call a expanded octet. And so should we expand the octet or should we leave it as an octet? And why would we expand the octet in the first place? Why not just leave it like this? Everything looks good here, doesn't it? Why would it be more stable? Yeah, typically the more bonds, the more stable. So that's one argument for stability. But we just can't go crazy. We can't just put in more bonds here, can we? I'd like to. Well, that's even better. because 4 double bonds should be better than 2 doubles. In fact, let's go triple. Take that lone pair. 2 triples and 2 doubles, even better, because, right, the more bonds, the more stable. In fact, I got 2 lone pairs here. I don't want to go extreme, but I mean, we could. We could go quadruple bond. Just take those lone pairs out of there, right? Just form more bond. And so we want to maximize bonding, but there's a problem with maximizing bonding, and that is it stable? Right. And so why did I stop at 2 double bonds? Why didn't I just keep going? And why did I form 2 double bonds in the first place? What makes this less attractive? This is all stuff from Chem 1A. You need, if this stuff isn't fresh in your mind, you need to refresh your memory. That is, you need to go back and review some of this, because you'll need this in Chem 1B. We're talking about reactivity. We need to know structure. We need to know composition. And so here, you know, what about this structure is not good? Formal charges. Good, you saw that. I didn't write the formal charges there, but you probably could see that the formal charges are a little weird here. What are the formal charges? Yeah, give me the non-zero formal charges. What's the formal charge on sulfur? Close. 2 plus. But formal charges, I have a convention. You know, and this is typical of formal charges. Formal charges are usually circled. And rather than doing a 2 plus, we just say plus 2, circle. Formal charge. And I'll do different colors. Actually, all these pens. Blue. Plus 2. So, what's the definition of formal charge? Well, that's an equation, but I mean, the equation for formal charge is, yeah, valence minus lone pairs minus half the bonds, whatever. But what does that mean? You know, physically. I can come up with an equation, but, you know, define it as that equation, but in terms of theory, you know, in terms of being and theory is a fundamental description. Theory is like a picture at the very basic level of what's happening. You know, what's happening here? And so you want to review that too. You know, what exactly is a formal charge? And so review that. But, you know, it's easy to calculate. Everybody can calculate it. It's a simple equation to calculate it. But what does it mean? Well, to me, this means that sulfur has lost 2 electrons. Do you guys remember I1 and I2? What does I1 and I2 stand for? Or IE1, IE2? Ionization energy. Do you remember successive ionization energies get easier or more difficult? They progressively get more difficult. And so if we tried to take a 3rd electron from sulfur, are we going to have an easier time or a harder time at that? Much harder time. And if you look at the data, it kind of doubles in terms of how much energy it takes to ionize the 2nd electron. And so here, a valence electron, the core electrons is like a 10-fold increase in difficulty. But to take 2 electrons from sulfur, is that an easy thing to do or a hard thing to do? It's a hard thing to do, and so that costs energy. Where did those electrons go? On these oxygens here. So basically these oxygens took electrons. One oxygen took 1 electron, the other oxygen took an electron from sulfur. Now, formal charge is defined more strictly. Formal charge is defined as the, you know, assuming the bonding is 100% covalent. Over here, the reason why they did the multiple bond is because now removing any electrons? No, so this seems perfect. Is now the formal charge is dropped to 0, so we don't have to deal with that I1, I2, ionization energy 1, ionization energy 2. And then we have electron affinities, but the electron affinities can't quite compensate for that energy. But there's a situation, I picked this one because this is one of the most difficult ones from Chem 1A. In order for this to double bond, what has to happen? Well, let's take a look. What's the hybridization on sulfur here? sp3. And so this bond would be an example of what? An sp3 on sulfur bonding to, this is for valence bond theory, to, what's the hybridization on oxygen? sp3. So this would be an sp3 sigma bond. If we go over here, a double bond consists of, well, this would be, what's the hybridization on this sulfur? sp3. What's the hybridization on this oxygen? sp2. So now we have an sp3 sigma bond, and you know, a double bond consists of a pi bond as well. What's the pi bond here? Is it a p pi bond? Here. It cannot be a pp pi bond. Why can't it be a pp pi bond? It can't be a pp pi bond because, let's just leave it off. Because if I do an sp3 hybridization, how many unhybridized p orbitals do I have left over? None. And so this cannot be a pp pi bond. This has to be a well, this is sp2, so I have a p orbital on the oxygen, and then I have to go to a d orbital on the sulfur. So this is an example of a pd pi bond. Now pd pi bonds, we need two of them here. We got to have a pd pi bond here and a pd pi bond here at tetrahedral angles. Well, the d orbitals are orthogonal to each other at 90 angles. And so this is already looking strained, unstable, having two pd pi bonds. And so maybe the reality is maybe one pd pi bond is okay. And so we have one double bond and three single bonds. Maybe that would be a little less. Here we can lower the charge, so and then only form one pd pi bond. Two pd pi bonds might be tough. And we're doing all this guessing because this is just pencil and paper analysis. If we want to do a full theoretical analysis of this, what theory would we use? What theory would we use to do a full theoretical analysis of the structure of sulfuric acid? Well, the theory of chemistry. What is the theory of chemistry that underlies chemistry? Quantum mechanics. And so we do a full quantum mechanical analysis. Now, quantum mechanics, the calculations are tough, but the computers are becoming more and more powerful. And it turns out that a full quantum mechanical analysis of sulfuric acid shows very little D contribution in the bonding. If there's very little D contribution in the bonding, then it's likely not like this. And so the Wikipedia structure is actually not the most accurate. From the latest data, this is in Petrucci, from the latest data, there is some charge. And these are the two extremes. We either have an octet or expanded octet. We either have some formal charge or no. What it turns out is there's a little bit of D contribution and some ionic contribution. Do you see over here the formal charge is all 0? If the formal charge is all 0, do we have any ionic bonding occur between neutral species? So 0 charge, 0 charge. Is there an ionic bond that will form? No. And so there's no ionic. This is purely covalent. But over here, this is covalent also. This is an sp3 sigma bond. That's a covalent bond. But in addition to the covalent bond, there is an ionic bond as well. How do you show the ionic bond? How are ionic bonds shown? They typically aren't. Ionic bonds aren't shown. All you do is draw the charges adjacent to each other. And so this negative oxygen is going to be attracted to this positive sulfur ionically. Do you see that? And so, in other words, we're going to have a significantly greater ionic character in this bond than in this bond here. And so, based on those quantum mechanical calculations, you know, there is a significant ionic contribution, and there isn't that much d orbital. So the true picture is between these two extremes here. Well, anyway, this is just to tell you to start reviewing bonding if this stuff, you know, and the more times, maybe the first time you heard this stuff, it just, right? And so this might be the second time, and then the third time, you know, a little bit more will sink in, and a little bit more will sink in. And so start reviewing this, you know, this hybridization stuff, covalent bonds, ionic bonds, because this stuff is going to be important for us in understanding chemical properties, chemical reactivity. Okay. All right. Well, anyway, what forms? In this particular reaction, you know, I wasn't expecting any of this analysis. This analysis was just to review some Chem 1A concepts. Since this is all reviewed, this is a good time to review. So this is your standard double replacement type reaction. We're going to form calcium sulfate and carbonic acid. Carbonic acid, you should know, immediately decomposes into H2O liquid plus CO2 gas. Calcium sulfate, what do you predict calcium sulfate? Would you predict that to be soluble, aqueous, or insoluble? Solid. Aqueous? Why would you be leaning towards aqueous? The solubility rules? Solubility rules are that sulfates are mostly soluble except for and so one of the things, calcium sulfate should precipitate. It should be a precipitate. And by analogy, I mean, calcium is 2 plus, sulfate is a 2 minus. Except in this case, sulfate is not trigonal planar. Sulfate is tetrahedral. And so it's more spherical in shape. And so the lattice will probably be a cubic lattice like this. Where the calciums form a face-centered cube, and the sulfates occupy holes in that lattice. And so we have that, and then we go on. This is what we call the complete equation, or what I call the complete equation. Then we want to go on to the ionic equation. The ionic equation is going to talk about things like electrolyte properties. For the ionic equation, we ionize or hydrolyze the strong electrolytes. And so calcium carbonate, do I leave it together or does it break apart into ions? We leave it together. Insoluble solids. Sulfuric acid, do I leave that together or break it apart? Break it apart because strong acids are strong electrolytes. And so what do I break it apart into? 2H plus and an SO4 2 minus? Is that right? No, this is not right. What happens is H2SO4 is a strong acid. And H2SO4, does it lose both protons at the same time? No, normally it loses just one proton at a time. And so if it loses one proton, we're left with HSO4 minus. Now, is that second proton going to be easy to break off? No, it's going to be more difficult because now we're dealing with a negative. Because the first one was easy. The second one, it's hard. Now, we know what's going to break off because the strong electrolytes are the strong acids, strong bases, and the soluble salts. Well, this is a weak acid. And so are weak acids going to ionize 100%? No. And so it stays as H plus and HSO4 minus. All right, AQ is so common. Sometimes they'll just omit AQ and write everything else, like solid, liquid, gas. Calcium sulfate, ionize or leave it alone. Leave it alone. And H2O, leave alone. CO2, we leave alone. Because the only thing we ionized was sulfuric acid, the strong acid. Everything else is not a strong electrolyte. And now we cancel out the spectators. There's no spectators, so the NIE is the same as the IE. Okay, we should indicate the driving force. So what's driving this reaction to occur? One is we have a precipitate here. Precipitation of calcium sulfate. Are there others? Yeah, gas formation. This is all for double replacement or monophos. And 3, yeah, it doesn't have to be strong, it just has to be stronger. So it could still be a weak acid to weak acid as long as it's going from stronger to weaker. So we'll go stronger acid, SA, to weaker acid, WA. That would be another driving force. So in this case we have all three driving forces that we were looking for, but really we only need how many driving forces? Only one is required. All right, since I'm doing this, let me erase some of this here. You get it? So in the homework, this is what I expect, you know, for metathesis style reactions. Let's look at the other reaction, magnesium nitrate. What's the formula for that? MgNO3, 2. Now, magnesium nitrate, like all ionic compounds, most of them are solid. So should I write solid here? I'm not going to write solid here. I could, but I know that there is water present, aqueous ammonia. So as soon as I mix solid magnesium nitrate with aqueous ammonia, what's the first thing that's going to happen? It's going to dissolve. Because you haven't memorized, nitrates are all soluble. Now, why do you think nitrates are all soluble? You know, at one end you have the nitrates. Nitrates are soluble. Acetates are soluble, right? Nitrates and acetates are soluble. Versus at the other end of the spectrum, you have phosphates and carbonates and chromates, which are typically insoluble. So what's the difference there? What's the connection? Do you see a pattern there? Nitrates versus phosphates. Nitrates soluble, phosphates insoluble. How come? Well, phosphates, the size is more tricky. Nitrates are actually smaller than phosphates, but there's something else. The charge. Phosphates are -3. Nitrates are -1. And so these are the things that our two-pronged approach that we're trying to accomplish. Not just straight memorization, because if you're just straight memorization, then you can only get so far. And so we expect, this should be soluble. There's water present. It's going to dissolve. We'll just call it AQ. Ammonia, NH3. Now, is this a metathesis reaction? You look at this, it doesn't look like a metathesis reaction because metathesis are ion combinations. Ammonia is not an ion. Ammonia is a molecular compound. But ammonia is a weak base. Weak bases are weak electrolytes. Weak electrolytes do what in water? Partially dissociate in water. And so what does ammonia partially dissociate into? Think about it. I'll give you. What does ammonia partially dissociate into in water? Okay, so ammonia dissociates into ammonium and OH. That doesn't balance, right? That doesn't balance at all. A lot of people, when I ask this question, they get N3 minus and 3H pluses. Does that look right? At least that balances. But does that look right? Not at all. And so ammonia, like all weak bases, do not dissociate. Ammonia, like all weak bases, partially hydrolyze. They react with water. And so ammonia and water will form ammonium and hydroxide. Now it balances. This is an acid-base reaction. Also, we have partial hydrolysis here, and that forms these ions. These ions can react. Actually, I know magnesium ions love hydroxide ions, right? Actually, I'll just write it like this so I fit the pattern. Ammonium hydroxide. If I write it like this, I have the AB plus CD pattern. So what do we form? We form magnesium hydroxide. This is a favorable ion combination. This precipitates out. And ammonium nitrate. Well, a lot of Chem 1A instructors, they don't like to write ammonia and water like this. They would prefer you write ammonium hydroxide here. But I don't want you to do that. I don't want you to write ammonium hydroxide. Even though that's what's reacting. What's reacting are ions. And the reason I don't want you to do that is because when we set up these reactions like this, you know, we want to do these reactions. And so if you're to go to the chemical supply place and say, I need some magnesium nitrate, no problem, magnesium nitrate. And then you ask, I need some ammonium hydroxide. Are you going to be able to buy a bottle of ammonium hydroxide off the shelf? No. The reason is it's unstable. In fact, the only way we're going to get the ammonium hydroxide is if we buy ammonia and have that hydrolyzed with water, which it already will. And so when we buy ammonia, there's a little bit of ammonium hydroxide. Just a little bit, but enough to have reaction. And so this is the reason why I want you to leave it as ammonia and water rather than write it as ammonium hydroxide. It's because you don't go to the store and buy ammonium hydroxide. You go to the store to buy ammonia. And in that ammonia, we have a slight contamination of ammonium hydroxide, which causes this reaction to occur. This is not really contamination. It's just what we expect to find in solution with it. And then we go. This would be the CE, we write the IE, and so on, the NIE. So let's go ahead and do that. I don't want to lose states here, so I just use ammonium hydroxide to figure out what the products are, and then I get rid of it. Magnesium nitrate, do we split that apart?
Yes.
Yes. It splits apart into magnesium, 2 plus, and 2 nitrate. Ammonia, do we split that apart? No. Actually, this is not balanced because we don't need one ammonium hydroxide, we actually need 2 ammonium hydroxide. To get 2 ammonium hydroxides, we'll need 2 ammonias and 2 waters. To produce, to precipitate, so So the driving force here, we just have one, and that's precipitation, magnesium hydroxide. In this case, do we have any spectators? We do, but I don't want you to cancel them in the ionic equation. I just want you to omit them in the net ionic equation. You can omit AQ again, but if you do that, you make sure you write in liquid, solid, gas, the alternate state. Since it gets quite repetitive to keep writing AQ. All right, that's it for today. Any questions? Yeah. All right, so tomorrow we're going to look at acid-base and redox reactions. So you can get a preview by looking at the PowerPoints for tomorrow.